Welcome back to the Deep Dive. Today we're jumping right into a huge topic for the future of safe AI.
That's right. We're talking about privacy in large language models.
And specifically, we're going to unpack VaultGemma 1B. It's a major release from Google that tackles AI's pretty serious data leakage problem using something called differential privacy.
And it is a serious problem. The core risk here is that LLMs are trained on, well, basically the entire internet. And they're really, really good at accidentally memorizing sensitive data they see.
You mean things like PII, personally identifiable information?
Exactly. They can just spit it back out verbatim. It's a huge privacy flaw.
So these incredibly powerful models can accidentally become these giant, leaky photocopies.
It's a pretty good analogy, yeah.
And the solution, according to our sources, is differential privacy, or DP. Why is that considered the sort of mathematical gold standard here?
Because it is provable. I mean, DP isn't just a suggestion, it's a rigorous mathematical framework. It fundamentally limits how much any single training example can influence the final model. It gives you a guaranteed mathematical bound on information leakage.
So it's an actual proof, not just a promise.
Precisely.
All right, let's get into the big distinction VaultGemma is making. We hear a lot about applying DP during fine-tuning, but the argument here is well, it's not enough.
It's really a false sense of security. The model sees most of its data during that initial massive pre-training phase.
Right, before any fine-tuning even happens.
So if the model has already memorized PII during pre-training, applying DP later doesn't just magically erase that memory. The vulnerability is already baked in.
Especially for open-weight models where anyone can get their hands on the weights.
That's the real danger zone.
Which brings us back to VaultGemma. What they're doing differently is providing an end-to-end privacy guarantee, right?
Yes, they trained the model fully with DP from the very beginning, from the pre-training phase on the same massive 13 trillion token dataset as the Gemma 2 series.
And they delivered a very specific, measurable guarantee.
They did. For VaultGemma 1B, which is now the largest privately trained open-weight model out there, they have a, let me get this right, a epsilon-lec 2.0 delta-lec 1.1 E10 sequence-level DP guarantee.
Okay, that is a lot of Greek letters and exponents.
Yeah.
For those of us who, aren't reading theory papers for breakfast, what does an epsilon of 2.0 actually tell us?
Think of epsilon as the privacy budget. The lower the number, the stronger the privacy. A 2.0 for a model this big is actually, it's a very robust guarantee. And delta is just the tiny, tiny chance that the privacy could theoretically fail.
So it's the mathematical proof that you're capping the risk.
Exactly. And the empirical proof is even clearer.
What did they find when they tested it for memorization?
Well, the non-DP Gemma models, they had detectable memorization. But VaultGemma, it showed absolutely no detectable memorization at all.
Wow. So it worked.
It worked. The DP approach, when applied from the start, it solved the leakage problem.
But there's always a trade-off in AI, isn't there? The sources talked about a utility gap. What do they have to sacrifice for this level of privacy?
Utility. Performance, basically. DP works by adding mathematical noise during training to protect the data points.
And that noise, while it protects privacy, it must hinder the model's ability to learn perfectly.
It does. It's just the inherent cost. So while VaultGemma is really impressive for a private model, its actual performance is comparable to non-private models from about 5 years ago.
Like a GPT-2 class model?
Yeah, something like GPT-2 1.5b. So that shows you the gap that researchers are still trying to close.
To even get this to work at scale must have been a huge engineering challenge. I saw mentions of new scaling laws and something called truncated Poisson subsampling.
Right, because DP training is just incredibly slow and expensive. They had to invent more efficient ways to do it. That subsampling technique, for example, is a clever way to build training batches to get the most learning done while still staying within those strict privacy math rules.
So they were maximizing efficiency under some pretty severe constraints.
A constant balancing act.
So what does this all mean for you, the listener? VaultGemma 1B isn't going to top the leaderboards for performance today, but it's a huge baseline.
A really powerful one. It gives the whole community an open methodology and a working model that is genuinely private by design. It's about accelerating safe AI research for everyone.
It really proves that powerful, large-scale, and provably private AI is technically possible.
Which leaves us with a really interesting thought to end on. If VaultGemma proves this can be done, what's the next big breakthrough needed? Is it in algorithms, data curation, or just raw compute efficiency? What will it take to finally eliminate that utility gap and make a private model completely indistinguishable from its non-private twin?
That feels like the challenge that's going to define the next few years of AI development.
Okay, so today we are diving straight into a problem I think we all face, just information overload.
Right.
And we're tracking a really interesting move from PLAUD, launched right ahead of CES.
A really strategic move. They haven't just put out one new tool, they've released two.
Exactly. A new AI note-taker pin and a new desktop application.
And that's our mission for this deep dive, to quickly unpack this dual approach. It's more than just specs. It's about understanding why PLAUD is moving from being this niche hardware company for physical meetings into the really crowded digital meeting space.
They want to own your entire workflow, basically, no matter where the conversation is happening.
That's the goal. So there are two prongs of attack here, the physical device, the PLAUD NotePin S,
The one you can clip on.
and then this new desktop client for all your virtual meetings. It's an attempt to bridge that gap between, the physical world and what's on your screen.
Okay, so let's start with the hardware. The NotePin S. It's the successor to a device that was already pretty popular.
Very popular.
Priced at $179, and it's really built for people on the move. But here's a question. If the AI is so smart, why do we still need a physical pin?
That's what's so fascinating. They're reinforcing the human element in all this.
Oh, so?
Well, the specs are great. 64 gigs of storage, 20 hours of continuous recording. It captures audio within about 10 feet. But the killer feature is the button.
The physical button.
The physical button, they brought it over from the NotePro. You can tap it while it's recording to highlight a specific moment.
So you're basically telling the AI, hey, this part right here, this is the important bit.
Exactly. It's you, the user, focusing the AI's attention on what you already know is important. It's that immediate human input.
That's smart. And for convenience, I see they've added Apple Find My support.
Which is huge for a small piece of essential gear like this.
For sure. And you still get that 300 minutes of free AI transcription every month with their service.
Right.
So let's shift gears and talk strategy. PLAUD has sold over 1.5 million devices.
Yeah, they absolutely crushed the market for in-person meeting capture.
But now, moving from the pocket to the desk, that means they're up against some heavy hitters. Why take on established players like Granola, Fathom, or Fireflies?
I think if they don't, they risk becoming obsolete. Those competitors are pure software. They specialize in transcribing and summarizing virtual meetings. So PLAUD has to standardize their whole offering.
And this new desktop client is how they do it. It works across most meeting apps, but you flag something specific about the Mac app.
Yes, the Mac app uses system audio capture.
Wait, hold on. Why is system audio capture better than just, recording your mic?
It's a cleaner signal. It pulls the digital audio feed directly from the meeting software itself.
So you get a perfect recording of the call.
A perfect, pristine recording. Not audio that's gone through your mic, picking up your keyboard clicks or, the coffee maker in the background. It's a much better source for the AI to analyze.
That makes a lot of sense.
And once it has that clean audio, it brings in all their AI muscle. It structures the transcript, creates notes, but it also supports multimodal inputs.
So you can add images, type notes.
Exactly. You're combining the audio with screenshots, with your own thoughts, all into one single comprehensive knowledge log.
So we connect this to the big picture. PLAUD is really trying to eliminate knowledge silos. They don't want your client meeting notes in one place and your Zoom summaries in another.
That's it. This is PLAUD's pivot from solving a hardware problem to solving the much broader problem of centralizing knowledge across your entire professional life.
So boiling it all down for the user, PLAUD is giving you an updated tool for your pocket and a really powerful integrated app for your desktop.
They want to be the one place for every piece of information you gather.
Right.
But this does raise a really important question for the future. As the AI gets incredibly good at capturing all the context from system audio and images, how relevant does that physical human act of tapping the pin to highlight a moment remain?
Will our manual input always override what the AI thinks is important?
That's something to think about.
And I think that's the final takeaway for you listening at home. Look at your own workflow. Think about which environment the precise 10-foot range of that physical pin or the unlimited clean digital feed from the desktop app is generating the most critical information for you right now.
Because that answer really tells you where the value of this whole launch lies. Welcome to the deep dive. Today, we are getting into something that feels like the future of how we interact with our computers.
It really does.
We're looking at a new piece of hardware, these wireless earbuds. from a company called Subtle.
And we've been looking at the TechCrunch reporting on their launch. The story here isn't just the earbuds, it's the AI inside them.
Exactly. And their whole mission is to solve the biggest problem for voice interfaces: noise.
Right, the ambient sound that just makes using voice assistants in public almost impossible.
So let's just jump right to the key nugget, the big claim they are making.
Okay.
Subtle is asserting that their voice buds deliver 5 times fewer errors than AirPods Pro 3 when paired with OpenAI's transcription.
That number is, well, it's the whole game, isn't it?
It's a massive claim.
It is, and it's basically an admission that for all the AI smarts we have now, the hardware most of us use just isn't up to the task in the real world.
But let's push back on that a little. Is that even a fair comparison? I mean, AirPods are made for music, for calls, for noise cancellation, not specifically for transcription.
That's the point, though. They're competing in a category they basically invented.
A league of one.
Exactly. Subtle CEO Tyler Chen says the reason voice hasn't taken over is because of that environmental noise, but also the social awkwardness of it.
Right, of talking to your phone on a crowded train.
And this AI is designed to fix both of those things at once.
So how are they actually doing it? What's the tech?
Well, they've been developing these specialized voice isolation models, I think, with partners like Qualcomm and nothing.
And they just bake that directly into these new earbuds.
Yep. So it's not just about you sounding clear on a phone call. It's about feeding a perfectly clean audio signal to the transcription engine.
And the demos seem pretty wild. TechCrunch saw it work in a really noisy setting.
Not only that, but it could apparently pick up whispered text.
Whispered text. Now that's a game changer.
Oh, absolutely. I mean, if you can just whisper a note to your device and have it be perfectly accurate, the whole privacy and social awkwardness problem just kind of disappears.
So this isn't noise cancellation, it's something different.
It's signal separation. It's
Yeah.
identifying your voice, even a quiet one, and just filtering out everything else around it.
Okay, so let's talk about the product itself. What do you get?
The buds cost $199, and that comes with a year-long subscription to their app for iOS and Mac.
And that app pulls it all together: dictation, AI chat, voice notes. It's a whole system.
It is, and this is the really critical part. There's a custom chip inside.
What does that do?
It lets the buds wake your iPhone directly, even when it's locked in your pocket.
So it removed that friction. No fumbling for your phone to start a voice command.
That's what delivers that truly seamless experience they're promising,
Right.
and it puts them in a really interesting competitive space.
They're not just up against Apple and Samsung anymore.
No, they're also fighting specialized dictation apps. WhisperFlow, Super Whisper, and even new hardware like those note-taking rings from Sandbar and Pebble.
It's a battle for who owns that unified voice assistant interface.
It really is.
So the critical takeaway here for you, our listener, is that this isn't really about better earbuds for music.
Not at all.
It's about selling a solution to a real-world problem. They're using specialized AI to turn any loud, chaotic place into your own quiet digital workspace.
Which leaves us with a really fascinating question, I think.
Go on.
Well, if a specialized device like this can deliver 5 times better accuracy, does that mean the future is all specialized hardware for different AI tasks?
A different gadget for everything.
Maybe. Or does this just force the big general-purpose players like Apple to get serious and build this level of noise isolation into the next generation of AirPods?
And what happens when all of this specialized AI processing can just happen on the phone's main chip itself?
Exactly. Where does the hardware go then? That's something to really think about. Okay, so for today's deep dive, we're jumping into one of the biggest bottlenecks for high-performing language models: context length.
Right. When you give an LLM a really long document, we're talking 100,000 tokens or more, the cost just goes through the roof.
And we got a fascinating paper here that tackles this head-on. It's called End-to-End Test-Time Training, or TTT-E2E.
And that cost escalation, that's really the central conflict. I mean, today's best models, the Transformers, they're built for almost perfect lossless recall. To do that, they use full attention.
And that's where the problem is.
Exactly. You double the document length, and the computation required, it quadruples. That quadratic cost is why long context has always been so hard to do efficiently.
This is where the paper makes a really crucial pivot. They don't see it as an architecture problem to be solved. They frame it as a continual learning challenge.
Hmm.
They use this great analogy, that humans don't recall every single detail perfectly. We compress experience into intuition.
And that's what TTT-E2E tries to make the model do, compress the context right into its weights.
So how does that actually work in practice? I mean, how do you get a model to build intuition?
Well, they start with a pretty standard architecture, a transformer, but it uses sliding window attention, or SWA.
Okay, and for anyone who doesn't know, SWA just looks at a local window of tokens, right? Maybe the last 8,000 or so.
Yeah.
To limit that quadratic cost.
Precisely. But that creates a new problem.
You lose the global context. That's the trade-off. So how do they get that long-range understanding back?
By forcing it to keep learning. Right at test time.
During inference.
Yes, that's what they call the inner loop. As the model is reading the text, it's constantly predicting the next token, and it uses the loss from that prediction to immediately update its own weights.
So it's actively writing the long-term context into its own memory, its parameters as it goes.
You got it. It's bypassing the short-term limits of the sliding window.
That sounds like it would be incredibly slow during inference, though. Aren't you just moving the computational cost from one place to another?
You would think so, but that's where the end-to-end part is so clever. There's an outer loop that happens during the initial training. They use meta-learning to basically optimize the model's starting weights to be a super efficient student for this test time process.
So you're pre-training the model on how to learn quickly from a new document.
Exactly. And to keep it fast, they're really smart about what they update.
Right. The paper mentioned they only update the MLP layers and only in the last quarter of the model.
Yep. They freeze the heavy attention and embedding layers. The MLP layers are where knowledge is stored most densely, so updating them gives you the biggest bang for your buck in terms of memory compression without the prohibitive cost.
Which leads to what seems like the holy grail here, performance that scales but with a constant cost.
That's the big result. Looking at their graphs, TTT-E2E's performance, its test loss, it scales with context length up to 128K tokens in almost the exact same way as a full attention transformer.
And other constant cost methods like Mamba or gated Diltonet, they just can't keep up. Their performance drops off in those longer contexts.
They really do. And on top of that, TTT-ETE gets constant inference latency, sort of like an old RNN. The paper says it's about 2.7 times faster than full attention at 128K context.
What's really fascinating to me is where that performance gain comes from. It's not what I expected.
Go on.
It actually performs better than full attention, and the advantage mostly comes from the earlier tokens in the sequence.
Right. Because its weights are so focused on the immediate task, the present mini-batch. A static model with full attention has to kind of, prepare its weights for all possible futures at once, which is a much harder learning task.
Okay, but there has to be a catch. There's always a trade-off.
There is, and it's a classic one. This kind of compression is lossy.
So tasks like needle in a haystack, where you need perfect specific recall.
It has a definite Achilles heel there. Full attention still blows everything else out of the water on those retrieval tasks.
Yes.
You're absolutely trading perfect memory for this massive gain in speed and efficiency.
So in the end, they've basically engineered a memory hierarchy. You have the SWA for short-term, in-the-moment memory.
And then the updated weights become this dense, compressed, long-term memory. It's a really elegant balance.
It really is. And it leaves you with a pretty provocative thought to wrap up on.
Mm-hmm.
If TTT-E2E is already showing an advantage over full attention on those early tokens, before the test time training has even really kicked in, what does that say about the power of meta-learning for just model initialization, about just learning to learn?
It suggests that initial training gives the model a fundamentally better starting point, that it might have an edge even when it's just processing short sequences, something to chew on.